Hello and welcome to lecture 25. Here we're going to discuss torque. This is the first section in chapter 8 and this introduces the concept of rotational dynamics. So that means we're really going to focus on forces for rotation. Okay? Now, specifically, we're going to really talk about the rotational equivalents of dynamic quantities that we have seen before. Because we've already talked about forces for circular motion. Think a banked turn and a car going through that turn. But no, now we're talking actually about the rotational equivalent of force. Well, I bet you can guess what it is. That's torque. That's what torque is. All right? It is the rotational equivalent of force. You can think of torque as rotational force. And we'll see, for example, in a couple of sections, when we introduce Newton's second law for rotation, torque plays the same role that force did. Okay, so we're replacing F with the letter for torque. Okay, all right, so with that out of the way, let's define how we calculate torque and kind of how we make sense of it as leverage and the idea of a lever arm or a moment arm. Okay, all right, so our key terms: moment arm, line of action, and then the torque vector. Okay, so here's the idea. Here we have some just kind of general shape. It could be anything, right? It doesn't have to be a clean normal geometric shape. It could be a potato. Okay, and we're thinking about a particular force applied at a particular point relative to a rotational axis. Okay, in other words, this is the pivot point. You know, maybe there's a nail through this potato and the potato is free to rotate about that point. Okay, and then we're applying a force here at this particular angle as shown. Okay, so what do we want to consider? Well, the moment arm is the measurement of leverage length. Okay, so if I have, for example, a wrench or a lever, the length of that tool, real life tool, would be the moment arm. Okay, that's just the physics term for that idea. Okay. Specifically, it is the component of the displacement vector that is perpendicular to the applied force. That'll become more obvious in the picture in just a moment. Okay? And the displacement vector is just the vector that points from the pivot to the location of the applied force. Okay? And for every force, there's a corresponding moment arm. And for every force, you will see there's a corresponding torque. It's very similar to when we talked about work, and it was one work per force. It's going to be one moment arm and one torque per force. Okay, but I don't want to get ahead of myself because I haven't really shown the equation for torque yet. But regardless, it's one per. Okay, now the line of action is just a line that is parallel to F, simply put. It's just a line that it's more like an axis than a vector, and it just runs parallel to the force vector. Okay, that applied force. What it does is it assists in drawing the right triangle that shows which components of force, it should say which components of R, which components of R are perpendicular to F, okay, or which component of R is perpendicular to F, okay? All right, so here's that displacement vector, okay, the one that was mentioned. Let's add some notation to this figure. Okay, so what's going on? Well, first of all, we have components. All right, now you should be familiar with the components on force, so let's talk about them first. This is just the tangential component and the radial component. Notice here I'm defining radial component as away from the center, all right? So if this is our center, right, our center of rotation, it doesn't matter, right? Just like we can define positive x up or down, well, positive y, I suppose, up or down, right? But it's still going to point along the direction of the radius, so radial is still a good name for it. But these are vectors we've seen before. Or rather, these are axes we've seen before, the tangential axis and the radial axis. So it makes sense to think of a particular force vector, here one that is neither entirely tangential nor entirely radial, and think of it as having both tangential components and radial components. Okay? All right. So that makes sense. But relative to what? Well, of course, relative to the radius. Here, though, I'm not calling this r vector the radius. Instead, I'm calling it a displacement vector because it's a little bit more general because it's relative to the rotation axis, which is just the pivot. I think that's a good way to think about it. All right. So it's just the vector that points from the pivot to the actual point P where the force is applied. That's all it is. That is our R vector, our displacement vector. Okay? Here's the aforementioned line of action, right? Just runs parallel to the force vector, right? And look what it does. If you draw that line and then form a right triangle, then you're going to get a component of R that is, well, what? That is perpendicular to F, and then another component of R that is parallel to F. And that's what's showing up here. Notice this notation. This is the same displacement vector R, and this is the parallel component. And this is the perpendicular component. Well, the perpendicular component, that's the one we care about. That is actually the moment arm. Because in other words, this distance there isn't helping our leverage at all. This distance, this parallel component of the displacement vector, the distance from the pivot to the applied force, is useless in creating leverage. All right? Case in point, think what would happen if the force vector was entirely in the radial direction. Well, in that case, the force vector would only have a component that was parallel to the displacement, and it could not create rotation. Try opening a door by just pulling parallel to the hinge. It doesn't work, okay? You have to push at least partially perpendicular to the displacement from the hinge to the doorknob, okay? So that's the idea. That's why it's only the perpendicular component of the displacement vector that's actually called the moment arm that actually creates leverage. Now, that said, you can also think about the force and which part of the force actually does any twisting or turning, because that's the idea, of course. We are, after all, talking about rotation here. This is our second chapter on rotation. So if we think about it, it's only the tangential component of force that actually can create rotation. So the radial component doesn't, okay? So we'll see that in the equations in just a minute. I just have one other idea I want to cover first. And this idea is kind of a follow-up on when I talked about the direction of the rotational acceleration vector alpha, if you recall, and the rotational or angular velocity vector omega, and how we can determine their direction. At least we can determine omega from the right-hand rule. So if something is spinning in the counterclockwise direction, you take your right hand, do this with me, take your right hand, curl your fingers in the counterclockwise direction, your thumb points up. That means something that's spinning counterclockwise has an angular velocity vector that points up. Well, torque is quite similar. All right, so if something is twisting in the counterclockwise direction, then tau points up. Okay, it's the same idea. It's the same idea. Okay, and so you can also think about it as taking the basically the palm of your hand faces in the direction of force. Notice the hand here. The direction of your fingers point in the direction of the displacement vector. So from the pivot to the location of applied force. Notice the hand here, right? So I'd be pointing my fingers along the direction of R. I'd then point my palm in the direction of F, and then my thumb will naturally point in the direction of torque. Okay? So notice it's this kind of curly looking T thing for torque. I'll talk about that letter in just a second. All right? So one way you can do that, one way it's often described, is you curl your fingers in the direction that the force is pointing, right? So you have your palm pointing, or you have your fingers pointing in the direction of R, and then you curl them towards F. And as you do that, see how these fingers are pointing towards F? As you do that, then naturally your thumb will point in the direction of torque. Okay? So it's the same idea as this, right? But it's kind of a slightly different way of thinking about what you're doing with your hand. Okay? All right, and this is just showing it again. All right, this one also shows that torque points in the same direction as angular velocity, which we just revealed, right? And there's also something called L, which is angular momentum, and we'll find that it also points in the same direction. So that's why I included this figure, because it's good, right, to see that all three of them are parallel. It's a good reality check. Okay, so here's the equation for torque, right? Here's the one we were using in this class. Torque right here, and by the way, we only really are ever going to calculate its magnitude. It's good to kind of have some idea about what do we mean by the right-hand rule and direction, but we're not going to ultimately deal with something called the cross product, at least not in this class. In the calculus supplement we would. And so for all intents and purposes, we only care about the magnitude of torque. But the other thing I have here is that letter, that curly T, is actually the Greek letter tau. and you say it like tau. Okay, so torque is always represented by the letter tau. Okay, all right, so how do we calculate it? Well, it's the displacement vector times the force times sine of the angle between the two. Okay, do compare that to work, because remember what work was? It was r times f times cosine of the angle between the two. Man, work and torque are calculated very similarly, aren't they? The only difference is that torque is sine of the angle between the two vectors, and of course work was cosine of the angle between the two vectors. But if we just say, oh, one's sine, one's cosine, that's helpful for memorization, but that does miss the point, because the point is this. Work only cared about, if I'm going to put it that way, only cared about the component of force that was parallel to the displacement, while torque only cares about the component of force that is perpendicular to displacement. Okay? So for work, you got more work when your force was more parallel. For torque, you get more torque, more twisting, or more ability to twist if your force is more perpendicular. But that makes sense, because think about the door. I open a door most efficiently if I push or pull on the doorknob in a direction that is perpendicular to the vector that points from the hinge to the doorknob, right? Of course we do. We take that for granted. Okay? So torque is best when the force is perpendicular. Okay, so here's the idea then. This right here, which sometimes we often will just calculate it by plugging in the angle if it's given, but we might think about it in terms of the component. Right here, this comes directly from the picture. This is the idea that it's the entire force vector multiplied by the component of the displacement vector that is perpendicular, there's that symbol for perpendicular to the force. So that r perpendicular, what do we call that? What's the name for that? The moment arm. Okay, so it's the moment arm times force. On the other hand, it's the, or we could, the other way to do it is it's the entire displacement vector times the tangential component of force. Okay, because of course, think about it, right? Because r perpendicular is just r sine theta, right? Likewise, ft is just f sine theta. So it doesn't matter which one you're taking a component of, you're going to get the sine theta either way. Okay? All right. All right, and furthermore, we often are going to talk about multiple torques acting on an object. That's kind of the whole purpose of this lecture in terms of the actual practice. And so in that case, torque net is just the sum of individual torques. Okay, so let me put all my labels in here. Displacement, applied force, angle between R and F, and then here we just put that, this is just the sum of individual torques. This notation is just summation notation. You've probably seen it. If you hadn't, it just means like tau 1 plus tau 2 plus tau 3 plus tau, right? You get the idea. Tau 4 or 5, so on, okay? But wouldn't really ever have 5 torques, okay? Maybe 3 really, maximum, okay? All right, let's do some practice. Okay, so there's only just one type of problem here, pretty straightforward. Just going to be involved calculating torque, okay? Potentially summing torque values. All right, example 1. 2 thin disc-shaped wheels of the smaller radius, RA, 30 centimeters, and the bigger radius, RB, 50 centimeters, are attached to each other on an axle that passes through the center of each as shown in the figure, right? Okay, so what is the net torque on this compound wheel? Okay, so compound wheel is what I'm calling these 2 disc-shaped things. We can think of this, kind of, maybe this one comes up 3D a little bit higher than the other one, okay? So anyway, this compound wheel, due to the forces shown, each of which has a magnitude of 50 newtons. Okay, so it's shown here in the figure. This is a 50 Newton force. This is a 50 Newton force. Okay, so let's think about something. This force wants to rotate our compound wheel in what direction? Well, it wants to rotate it in the clockwise direction. Okay. Meanwhile, what direction does this force want to rotate it? Well, this one wants to rotate it in the counterclockwise direction. So that means that these 2 forces, FB and FA, are going to create opposing torques. Okay? So then let's think about what is the net torque due to these 2 opposing torques. Okay? So we're going to need to think about the components of FB, since it is not entirely tangential. So we only care about its tangential component. So this is the one we're going to focus on. Here I'm showing the torque vector. All right. I'm showing it as pointing into the page. All right. Because I'm assuming maybe that this vector is going to create the larger torque. But let's see. Okay. So let's take torque net as tau A plus tau B. So this would be the torque created by force A. And then this torque B, would be the torque created by force B. See how there's always one torque per force? Okay? All right, we just sum them up, and it's a scalar equation. All right, so then we have, let's think about the signs, okay? So for torque A, that's this one here. So this wants to create counterclockwise direction, so that would be positive, okay? And it would be force A times RA times sine of 90 degrees. Why 90 degrees? Because this force is entirely tangential, and so you get so sine of 90, of course, is 1. So when a force is entirely tangential, you get the whole magnitude. It's force times radius, okay? That's your maximum torque case in terms of angle. All right, but again, why positive? Because you might be wondering. Well, because with any rotational system, the convention is to define counterclockwise as positive, okay? That is the natural positive direction. Just like we assume that to the right is positive x and up is positive y, right? There's no reason we can't change the system, but the basic assumption is to the right is positive x, up is positive y, okay? Likewise here. Counterclockwise is positive theta, okay? Okay, simple as that. Clocks turn in the negative theta direction, okay? All right, so that's positive. So this torque that wants to create a counterclockwise rotation, and it would if it was on its own, of course, well, that's just FB times RB times sine of 60, okay? So why sine of 60? Well, because 60 is the angle between R and F. This would be R. This would be F, see? And so the angle between them is the 60 degrees. So it's sine of 60. Now, of course, we could also take cosine of 30. They'd get the same answer, okay? And you could see that by just thinking about this right triangle. All right, so we plug in our numbers that we haven't yet. So 50, 30 centimeters, 50 and 50 centimeters, because this is on the bigger radius, RB. All right, and then we get negative 6.65, okay? So that's telling us that our torque is actually going to be in the negative direction. This force does win out, okay? So our torque is primarily in the negative direction, okay? And actually, that is consistent with the way it was drawn here, because this is actually assuming that it's into the page. This notation, by the way, means into the page. You're not required to know that. It's not necessary for this class. But this is like a vector notation showing the torque points into the page. And again, you could confirm that with your hand, right hand, twist your fingers in the direction that we found out the net torque faces, and then your thumb would point into the page. Okay. Well, in B, we're asked, if the goal was to achieve a positive 9, okay, so that would actually be counterclockwise, Newton meter torque, and FA and FB remain unchanged, so they're still both going to be 50, what angle would FB need to make with the tangent line, okay? So that would be this angle for the larger wheel's perimeter, okay? So instead of 30 degrees, what angle would FB need in order for the net torque to be positive 9? Well, that's a pretty big difference, right? Because right now it's negative 6. So that means we need our torque to change by almost 15 Newton meters. And quick note here, torque has units of Newton meters. When have you seen units of Newton meters before? Work, of course. But it should have the same units as work, because after all, it is force times distance, just like work. Now, here's a quick caveat that I want to make clear here. Torque is not interchangeable with work. The main reason being that torque is a vector, work is a scalar, okay? But beyond that, there are fundamental differences between torque and work, okay? But the units for torque are Newton meters, okay? So let's get that, our 15 Newton meter difference in torque. How are we going to do it? Well, essentially, we need this force here to be much less effective, okay? Because if you think about it, this force could certainly create enough torque, because it's 50 times 0.3. If I take 50 times 0.3, about a third of 15 is going to be greater than 9. So in other words, if this force was entirely radial and thus was creating no torque, then this force on its own would have more than enough ability based on its moment arm and its magnitude to create a torque of larger than 9 Newton meters, okay, in the positive direction, the counterclockwise direction. So that means that we should expect our angle to be somewhat close to 90 degrees, but not quite there, okay? All right, and this is just pointing out that negative means clockwise, okay? So part B, we want a net torque of 9 Newton meters, okay? So we're going to set this up, all right? This is going to be our torque B, all right? And then we just go ahead and solve for theta, because this is our unknown here. All right, notice I've plugged in all of our known values. We're going to take sine inverse, because I'm isolating that theta. All right, and we get 13.9 degrees, okay? Because essentially what I calculated, let's see which one. Oh yeah, so I actually calculated the angle relative to the radial direction. So I say here, what angle would it make with the tangent line? Well, the tangent line would be this way. So actually the value I asked for would be 90 minus 13.9. So let's see, that would be about 76. So about 76 degrees, okay? This angle as given, theta, of course, is, based on the definition of torque, that would be this angle, the angle with the radial direction, okay? All right, well, you get the idea. Okay, so let's do a quick concept question. The dumbbells shown are all the same size and mass, and the forces shown are all the same magnitude, ranging from largest to smallest, the torques, tau 1, tau 2, and tau 3, about the midpoint of each connecting rod. So this is our pivot point in each case. Okay, so let's consider what's going on. So we're just going to use our definition of torque, radius times force times sine of the angle between the two. This one's definitely the greatest. Why is that? Well, because look, all the forces are 90 degrees. Sine of 90 degrees is 1. All right, so that's our maximum case. So this one right away we know is going to be greatest. So what about these two? What is the difference between these two? Well, nothing. Because look, sure, this one points out and this one points in, but in both cases, the tangential component of that force is the same. Well, the tangential component's the same and the moment arm is the same, okay, right? Or really the displacement vector is the same, then those two have to be equal. These two torques have to be equal. They have to be because there's nothing different between them. So then if we were to rank them from smallest to largest, 2 and 3 would be tied and 1 would be the greatest. Okay? So it doesn't matter if the force points in or it points out. It only matters at what angle it points relative to the tangent. Okay? Okay? Oh, I'm starting this one here. So last example here. A rod is pivoted about its center. Okay? So it's kind of similar to the example 1, but now it's a rod. Okay? 5 Newton force is applied 4 meters from the pivot, and another 5 Newton force is applied 2 meters from the pivot, as shown. The magnitude of the of the total torque about the pivot is what? All right, so we're just going to find the total torque. All right, so same thing, sum of the torques. Okay, torque 1 and torque 2. Okay, so let's think about it. Are these torques, is one opposing the other like in the wheel? Well, actually they're not, right? Because think about it. This force wants to rotate the wheel in what direction? The counterclockwise direction. What direction does this force want to rotate the wheel? Also the counterclockwise direction. So these forces are cooperating. They're working together. So they're both going to be plus, okay, because they're both counterclockwise. Okay, just the way I've defined it. Positive theta is counterclockwise. Okay, so it's just F1 times 4 meters times sine of 30. Okay, this one just F2 times 2 meters times sine of 30. All right, well, they both have a 5 in common because F1 equals F2. Sine of 30 is shared in common. So the only difference is the length of the displacement vector. So then it's just 4 plus 2. And then we get everything together. We have a net torque of 15 meters. Simple as that. Okay? So obviously calculating net torque is sort of a small-ish question. It's usually part of a bigger problem. We're certainly going to see it when we deal with using Newton's law in rotational form in a later section of this book. But it was kind of an important introduction, and certainly, it's a new variable, torque. And so I'm glad we had a lecture to focus on it as just introducing what it means and what the heck is torque. Okay? All right, well, thank you so much for watching this lecture video. I hope it was interesting. You can check out further examples for practice and stay tuned for more lectures from this chapter.